Well, thank you very much, Leah, and thank you very much to the Institute for Molecular Science and Engineering for organizing this series. Today, Federico Pezzi and myself are going to discuss some of the factors that are governing the development of solid-state batteries based on garnet electrolytes with lithium metal anodes. Due to the big background levels that arises from this institute, we have divided the talk into sections. The first one is related to a broad context and the motivation for solid-state batteries. And later, Federico will give you some of the highlights of the latest research that we are doing in this area. So, as you all know, the energy production has been mainly based on fossil fuels with a very little contribution from renewable sources. Indeed, if we look to the data from 2017, the less than 25% of the global electricity was produced from renewable sources, and less than 6% of the thermal energy was produced from renewable sources. This high dependency on fossil fuels has led to a massive emission of pollutant gases, including greenhouse gases. If we look to the global greenhouse emissions since 1990 to 2018, we can see that 76% of the emissions come from CO2, 60% from methane, mainly from agriculture, and 6% from nitrous oxide, mainly from transport and industry. If we look to the global CO2 emissions by sectors, we can see that mainly most of the emissions from CO2 comes from the production of energy. Indeed, it's 72% of the global emissions arise from the production of energy associated to electricity and heat generation, also transport, and also manufacturing and construction, among others. So the connection in between the production of energy and the emissions of CO2 has led to a continuous increase of the CO2 emissions over the last years, and we have reached levels that are in the range of almost 35 gigatons per year. This continuous increase of CO2 emissions have only seen some drops associated to a lower energy demand in particular historical events such as the World War II or the financial crisis in 2009. It's interesting to see how they dropped during the last year due to the COVID pandemic 19. So what are the problems, the big issues associated to this high amount of greenhouse emissions? There are two main important consequences. The first one is the global warming. So the average temperature of the Earth's surface has increased almost for 1 degree since pre-industrial levels, and that has a huge impact on the environment and the ecodiversity. And then we have to look also at the effect of such a high amount of pollution in the air that has a big impact in the health. In fact, 9 of 10 citizens in the world is breathing high levels of pollution every day. And that has led to 7 million people dying prematurely every year. This has been associated to increase in lung diseases such as pneumonia, cancer, and other respiratory diseases, but also to brain strokes and heart diseases. So if we don't do anything about it, the previsions are that we can reach 150 gigatons of emissions of CO2 annually in 2100. This can lead to an average temperature rise in the surface of the Earth in between 4.1 and 4.8 degrees Celsius, which can have consequences that are still not known, but very, very important for our life in the Earth. Trying to stop this, several countries signed an agreement, the Paris Agreement in 2015, in which we agreed to keep the warming of the Earth below 2 degrees, but that it was much better if we could keep it below 1.5 degrees. In order to do this, we have to drastically reduce our CO2 emissions, and we must reach net zero CO2 emissions by 2050. This requires a transition to a completely new energetic model in which we have to mainly use renewable power and associated to efficient ways to storage energy. This transition is feasible, first because we are having more and more efficient ways to to use the renewable resources, and also because the renewable energy is becoming more and more cheap. Indeed, only in 2 regions in the world, the cost of renewable energy is higher than the average cost of electricity. In the rest of the world, it's at least 26% lower. We are expecting this to decrease in the coming years, not only related to solar energy, but also in wind, offshore and onshore. This is going to be also associated to the increase in the demand. As 2 days ago, Boris Johnson said that every home in the UK will be powered by wind farms by 2030. The problem is that if we are depending on renewable energy, the generation of energy through renewables is very intermittent and also very unpredictable. And therefore, we need systems that allow us to balance the peaks on energy production from renewables with the peaks on energy demand in the society. So we can achieve that using storage technologies. And from the different storage technologies, the electrochemical storage is the one that is going to be the focus of this presentation. Electrochemical storage is based on electrochemical devices in which we have 2 electrodes in which a redox reaction take place. Both electrodes are separated by an electrolyte that is an electronic insulator, so the electronic flow goes through an external circuit, but it's a good ionic conductor, so we can maintain the charge neutrality in the system. One of the good things of electrochemical storage is that it's very flexible. So we can use it for storage of high power grid storage applications, but also we can use it in portable electronics on electric car. Actually, electrifying transport is going to be one of the most important challenges that we have to face in the next coming years. Indeed, the UK plans to bring forward a ban of fossil fuel vehicles by 2030. In this sense, secondary lithium-ion batteries are to play a very important role. Secondary lithium-ion batteries were developed by Goodenough, Whittingham, and Yoshino, and they won the Nobel Prize last year in chemistry because of this. In secondary lithium-ion batteries, what we have is 2 electrodes. During the discharge, the lithium ions, they intercalate from the anode and intercalate into the cathode, and the electrons flow in the same direction. And during the charge, the lithium ions, they intercalate from the cathode and intercalate back in the anode. In commercial batteries, the anode is graphite and the cathode is a transition metal oxide that is a layer oxide, typically lithium cobaltite. Both electrodes are separated by a liquid organic electrolyte. This one in particular is typically lithium iron phosphate in ethyl carbonate, in methyl carbonate. And also there is a separator that avoids physical contact between both electrodes and therefore avoiding the short circuit of the cell. Although all portable electronics that we have nowadays are possible thanks to secondary lithium-ion batteries, they still have a lot of limitations. And most of them comes from this liquid organic electrolyte that we are using. There are 2 main limitations of this liquid organic electrolyte. One of them is the fact that it has a very low electrochemical stability window. The electrochemical stability window of the electrolyte limits the application of electrodes that can provide high cell voltage to the cell, what limits also the energy and power density that we can get from a battery. In an unstable electrolyte, what we have is that the LUMO of the electrolyte and the HOMO of the electrolyte have to be above and below the electrochemical potential of the anode and the cathode respectively. If this is not the case, like in this figure here, if the electrochemical potential of the anode is above the LUMO of the electrolyte, this can be easily reduced by the anode, and therefore it can lead to a degradation of the electrolyte or the formation of a solid electrolyte interface, typically called a SCI layer. If the HOMO of the electrolyte is above the electrochemical potential of the cathode, this can be easily oxidized by it, and it will have a similar effect than before. And therefore, the open circuit voltage that we can have in our battery is going to be limited by the length of the energy bandgap between the HOMO and the LUMO of the electrolyte. In the liquid organic electrolyte that we are commercially using nowadays, it has an electrochemical stability window that is poor at low voltages. In fact, it's not stable against in contact with graphite, that is the commercial anode that we are using nowadays. That initially prevented the commercialization of secondary batteries, and then it was discovered that by the addition of additives such as ethylene carbonate, we can stabilize an SCA layer that is thin, but also is electronic insulator, so that doesn't allow the continuous reduction of the electrolyte, but is permeable to the lithium movement, and therefore allows for the reversibility and cyclability of the batteries. The second big problem that these liquid organic electrolytes have is that they have a high flammability. And so they have severe safety issues. This high flammability is associated to thermal runaway issues that can happen in the batteries. That is a rapid increment of the temperature associated to different issues like lithium platinum on the graphite, gases evolution due to overcharging in the cathode side, or short circuit of the cell due to fracture of the separator. I'm sure most of you have seen Tesla cars in flames, but also problems with mobile phones. So these two limitations that are the electrochemical stability window and the safety are limiting the applicability of the lithium-ion technology that we have at the moment. And what we need is to develop a new technology that allows us to have higher energy and power densities, but in a safe way. In that sense, solid-state batteries with lithium metal can promote a very interesting path. Why is this? Well, on one hand, is because if we use a solid electrolyte, we can add thermal, chemical, and electrochemical stability to the system, what it heavily increases the safety of the system. The second one is that if we have a good electrochemical stability window in the electrolyte, we can also use high energy density electrodes, and therefore increase very much the energy density and the power density of the systems. Also, there is the possibility of miniaturization. But one of the most important things of using a solid electrolyte is that they could allow to substitute the graphite that we're using as an anode nowadays by lithium metal that has 10 times more capacity. If you looked at this figure here, you can see that actually the energy density of lithium metal is in the same order than that of the fossil fuels. So the range of applicability to higher energy density applications increases a lot. Also, the lithium metal is very light, and we can stack cells easier, and so therefore we can achieve higher energy densities for the same volume. Indeed, for instance, the European Commission has in its roadmap that we need to substitute the flammable liquid organic electrolytes by 2022, and is also aiming for the incorporation of lithium metal and solid electrolytes together by 2030 in batteries. This potential of solid-state batteries has raised a lot of interest in industry also, and all of the car companies that are in the race for the electric vehicles have multi-millionaire projects in the development of solid-state batteries. As you can see here, also the rate of publications have increased exponentially in the last few years. So what have been the challenges, or what were the main challenges in the development of solid-state batteries? The first one is that we need to achieve similar lithium mobilities than in the liquid state, whereas in the solid state, ion hopping is thermally activated, and we are working at pretty low temperatures that can range in between -10 and 50 degrees C. We are aiming for conductivities that are above 10⁻³ siemens per centimeter, so 1 millisiemens per centimeter. And also, we need the electrolytes to have high stability, so we need them to have chemically, thermally, and electrochemically stable, mainly with lithium metal and high voltage cathodes, so we can develop batteries that have higher energy density. In the last few years, there has been a lot of research in this area, and we have here represented 3 families of electrolytes that have surpassed this 1 millisieverts per centimeter that is required for technological applications. In this sense, the sulfides have presented the highest conductivity, and in the case of the oxides, we have developed the garnet electrolyte that has performed with the highest lithium conductivity. We have achieved this by controlling the concentration of lithium vacancies and interstitials in a network of tetrahedra and octahedra that are sharing phases, so achieving a very high conductivity with low activation energy. This is achieved for a composition of 0.15 gallium per formula unit, as will be described later also by Federico. Here is just showing to you how this particular composition has reached the maximum conductivity within the garnet substrate. In the last couple of years, another family of compounds have raised a lot of interest, and these are the halides. In particular, the lithium chlorides have been able to be produced with very high lithium conductivities. As I said before, lithium conductivity is very important, and we have a click there. But another important thing is the electrochemical stability window of the solid electrolytes. If we look to the sulfides, that were the electrolytes that were presenting higher lithium conductivities, you can see here that they have a very narrow electrochemical stability window, and therefore they are going to be very easily reduced and oxidized by the electrodes. If we look to the chlorides, this electrochemical stability window increases a lot, and they are actually very good at high voltages, but they don't have good stability at low voltages, and they are not stable against lithium metal. The only electrolyte that seems to be stable against lithium metal are the garnets that create an interface that is kinetically stable with lithium metal. So what are the major challenges in developing garnet-based solid-state batteries? All of them are focused on the interfaces. On one hand, we have the grain boundary interfaces. We are working with ceramic materials that are polycrystalline, and therefore we can create a lot of inhomogeneities chemically in the grain boundaries that can induce very different lithium mobilities and inhomogeneous current distribution. The other interface of interest is the lithium metal with the garnet. I said before that is kinetically stable, and it may not form an SEA layer that is leading to a higher resistance, but during cycling of the battery, this interface is very dynamic. Since we are stripping lithium, we can create voids that then don't recover, and so we can have a very inhomogeneous interface in terms of contact. All this inhomogeneous distribution of current sources that I am describing can lead to a very soon nucleation and propagation of lithium dendrites that eventually leads to a premature death of the cell. Another issue is related to the cathode. In the cathode, we have a solid state battery, so we have all solid state interfaces, and while cycling the battery, there is a change in volume in the cathode that can lead to the lamination while we are cycling the battery. From now, I'm going to give the presentation to Federico, that is going to explain to you what are the results and the investigation that we have performed in trying to understand these interfaces for solid-state batteries based on garnet electrolytes.
Thank you very much, Ainara. I'm gonna share my screen. Well, first of all, I would like to thank Leah for organizing this and inviting me to this seminar. And thank you very much, Ainara, for a very nice and exhaustive introduction. So, as you said, in my presentation, I'm gonna be a little bit more technical, and I'm gonna show you some of the results that we've been collecting over the last few years. And as you will see in my presentation, there will be quite a lot of questions, but I will try throughout the presentation to answer those questions. And hopefully at the end of the presentation, you will have a better understanding of the factors that are governing the performances of garnet electrolytes. So first of all, as Ainara said, there are several problems associated with the use of solid electrolyte. So it's a must that we first of all understand the problems that are actually limiting the performances of garnet electrolyte. Once we understand those, we can actually find a way to overcome these problems. And if we unify these two things together, so a good understanding of the problem and an overcome of the problems, we can actually have a targeted engineering of the materials. So hopefully we will be able to allow the use of garnet electrolyte in practical devices. I'm going to give you a very brief outline of my presentation. I'm going to start with a very short introduction. I'm not going to go too much in details because I think Ainara did it very well. And then I'm going to talk about chemical and electrochemical analysis of garnet electrolytes. When I refer to chemical, I will mainly talk about surface analysis techniques such as XPS or top SIMS, secondary ion mass spectrometry. And when I talk about electrochemical, I will refer mainly to electrochemical impedance spectroscopy and galvanostatic cycling. And I will try to show you how by combining these techniques, we can actually extract a lot of information, for instance, on sample inhomogeneity. I will show you how some elements actually segregate in a specific area of samples, and then how these elemental segregation can actually have an effect on the bulk grain boundary conductivities and activation energy, and how a combination of the two can actually have effect on the dendrite formation and propagation, which is actually one of the main reasons why garnet electrolyte at the moment are not used in practical devices. I will start by a very simple slide in which I'm showing you what material we are actually working with. So as Ainara said, we are working with garnet electrolytes. The material we are using, it's got this formula here. It's lithium, gallium, lanthanum, zirconium, and oxygen. And we synthesize them in our lab using a salt gel synthesis. After the salt gel, the powder undergo a series of thermal treatment, which are actually done in a luminaire crucible. After that, we end up with pellet, round pellet of this kind of shape here, about 10 millimeter in diameter, which we polish down very finely, and we thermally etch them. Initially, we were doing a thermal etching in order to reveal the grain boundaries and collect nice HCM images, but I will show you how actually etching is also affecting the electrochemical performances of garnet electrolytes. So in these slides, I've just highlighted, I've just put in red some words because I'm gonna use these words quite a lot of time throughout the presentation. So we will talk about polished sample, etched sample, and also the role of a luminaire crucibles. And if we want to investigate electrochemically the material, we can then take these pellets here, sandwich them in between two lithium foils, and then we can enclose the cell in a coin cell and perform all our electrochemical measurements. So I'm going to start by showing the last slide that Ainara has shown. I'm not going to focus my attention on the cathode solid electrolyte side, but I will focus mainly my attention on the anode solid electrolyte side. So as Ainara said, the contact in between two solids can actually lead to high interfacial resistances if the contact is actually not perfect. So if we have got void at the interface. And if we have got void, we've got point of contact in which the current density upon cycling will be very high. And this could actually lead to the nucleation of lithium dendrites and the propagation through the solid electrolyte. And we will see that even the composition of the grain boundaries can actually play an important role in the propagation of dendrites through the electrolyte. So there is a need actually to optimize the interface between metallic lithium and the solid electrolyte in order to have an easier transfer of lithium ion from the metal to the electrolyte when we discharge the battery, and the other way around when we charge the battery. In the other groups in the literature, I've reported several ways of improving actually the contact in between the lithium and the solid electrolytes. I must mention to you that we use a technique called electrochemical impedance spectroscopy in order to have an idea of how easy actually the lithium ions can actually move in the area of our electrolytes. So by recording electrochemical impedance spectra, we generally end up with three semicircles, like I'm picturing here. One will describe the bulk, one the grain boundaries in between LLZO grains, and one will define the interface. So we want to have the semicircle defining the interface as small as possible, and that will indicate a good contact between metallic lithium and the solid electrolyte. So other group have actually used pressure or the use of interlayers in between the two cell components, and in that way they were able actually to decrease the interfacial contribution from the impedance spectrum. However, we are actually using another approach. As I mentioned you in the first slide, we are actually thermally etching our samples. Initially, we were doing it to have nicer SEM images, so to reveal the grain. However, by testing, by electrochemical testing the different sample, we noticed that if we were testing with electrochemical impedance a sample before its treatment, so before thermally etching it, the impedance spectrum, you can see that is actually governed by the interfacial processes. However, if we take the same sample, we etch it at 900 degrees for 30 minutes, we see that the contribution coming from the interface decreases of about 2 orders of magnitudes. So we go from 12 kilo ohm per centimeter square down to 100 ohm per centimeter square. So actually, this brought us to make ourselves questions. For instance, what is the role of thermal treatment in the electrochemical performances of garnet? And how is the surface of our garnet, how is that affected by thermal etching, and how we can actually see this effect in when we carry out electrochemical impedance or when we carry out galvanostatic cycling. And to do that, we decided to, to answer this question, we decided to carry out quite a deep investigation of the garnet surfaces. To carry out surface analysis, we can use a wide range of surface analysis techniques. The Department of Materials in Imperial has got a wide range of techniques available to use. We can, for instance, start from LLZO, which is low energy ion scattering, if we want to see the very top surface, the very first monatomic layer of a sample, and then we can use other techniques if we want to go down deep into the sample up to the bulk of the materials. In this presentation, I'm going to focus my attention mostly on XPS and TOF-SIMS. XPS is quite a common technique. However, TOF-SIMS is, for those of you that are not familiar with TOF-SIMS, I'm going to explain you very briefly how it works. It's first of all a destructive technique. We've got a primary ion beams that actually impact the surface of our samples. And by doing that, we break the surface of the sample in its chemical components, which are then ionized to form secondary ions, which are encapsulated in a time-of-flight channel and detected by a detector. So the advantages of using TOF-SIMS in lithium-containing material, first of all, are good lateral resolution, so we can have information, for instance, on the composition of grains and grain boundaries and so on. But most of all, is that SIMS can actually have got an high sensitivity for low mass element. So we can actually detect and follow lithium on the surface of our samples. So in that way, we can actually have, as I said, idea on composition, different composition, presence of secondary phases, corrosion layers, and so on. I'm just going to give you an example here on how SIMS works. In this experiment, I was trying to look at a LLZO pellet in which we evaporated a very thin layer of lithium. And with SIMS, I was trying to go through the lithium electrode to the LLZO pellet and see how the composition was changing at the interface. If you can see from the depth profile, when we are on the lithium, we do have a depletion of all the other garnet components, and as well from the elemental maps, we only see that we've got a lithium-rich surface. However, when we go through the evaporated lithium, we see the appearance of other features. And if we look at the high-resolution images, we can clearly see we've got information on the chemical composition of grain boundaries, which, for instance, appear to be rich in lithium and aluminium, but perhaps depleted in lanthanum. Or we can see the presence of secondary phases, this lanthanum aluminate here. In this region, we've got an enrichment of these two elements, but for instance, a depletion of lithium. So this is just to show you how powerful can be seams to study lithium-containing materials. So going back to the impedance I showed you earlier and the effect of thermal etching, we decided to carry out HPS in order to understand what was the role of thermal etching on LLZO. And what we can see in here is an in situ X-ray photoelectron spectroscopy measurement in which we were following all the garnet components and carbon. And what we can see, we were doing it at increasing temperature from room temperature to up to 800 degrees. And what we can see, especially from the carbon spectra, is that we do have the disappearance of a peak, which is actually attributed to carbonates when the temperature reaches 600 degrees. Same thing we can actually see from the oxygen spectra, in which we also see a decrease and the disappearance of the oxygen peak associated with hydroxide and carbonates. And also interestingly, we see a shift in the carbon-carbon peaks at lower binding energy, which can actually indicate a graphitization of carbon on the surface of our samples, and that can actually also have an effect on the electrochemical performances of garnet. So what we concluded by doing this experiment is that to start with the polished sample, we actually have got a layer of lithium carbonate that sits on top of the LLZO. And this obviously create a more resistive interface in contact with the lithium metal. However, upon heating up, we actually remove the layer of lithium carbonate and we improve the contact in between electrodes and electrolyte. So the question that arose now was, is this just a cleaning effect or there is something else going on? And to answer that, we actually did some seams on the samples here, on the polished samples. If you can see from the seams depth profile, we see an initial region, a surface region, which appears to be enriched in lithium, but depleted in all the other garnet components. And this actually seems to confirm the fact that we are looking at a lithium rich, which could either be lithium carbonate or lithium hydroxide on top of our samples. And if we take the same sample, thermally etch it, and repeat the seams, we actually see that we don't have anymore the corrosion layer on top of the sample. So far we were happy. We thought, okay, it's confirmed, it's a cleaning process. However, we looked more deeply at the seams map. And as you can see, if we compare the seams map, elemental map of aluminium, gallium, and lithium, for instance, of a polished sample, we see that we've got a segregation, especially of aluminium at the surface of the sample. And this is attributed to aluminium sitting at the grain boundaries and at pores that we've got on the surface. However, undergoing a thermal treatment, we see that the aluminium in the etched sample is much more homogeneously distributed, and we still do have a small segregation of gallium and lithium. So now you probably will ask yourself, why am I talking about aluminium? I was telling you in the first slide that we synthesize garnet with a gallium contact rather than aluminium. However, as you remember, I highlighted the fact that we are doing all the thermal treatment in alumina crucibles. And so we try to see the effect that actually eating up a LLZO sample in a alumina crucible could have on the content of aluminium. So we carried out low energy ion scattering on a pellet that was heated up in alumina crucibles, and we compared the aluminium content in the two sides of the pellet. So the top side that wasn't in contact with the alumina crucible, you can see that it's got a much lower content of aluminium compared to the side that was actually in contact with the alumina crucible. So we know now where the aluminum comes from, and if we look at the negative ions, so if we follow aluminum oxide and OH, we can actually clearly see that there is a segregation of these alumina species at the grain boundaries. If we look at the phase diagram actually of lithium and aluminium, we can actually notice that we can have a favorable formation of this phase lithium-5 aluminium oxygen 4 eutectic at a temperature very similar to the temperature that we use to sinter our pellets. So it could actually be a problem. The fact that the grain boundaries have got a different composition from the bulk is something that was puzzling us. So we decided to carry out electrochemical impedance spectroscopy, and to do that, we just don't use impedance spectroscopy, but we combine impedance spectroscopy with the Kramer-Kronex validation test, which is a test that we do in order to see the quality of our data and to see how good the fitting could actually be. And we also combine EIAs with distribution of relaxation times. So if you look at the orange spectrum, for instance, the orange impedance spectrum here, you can see that it appears to have only two semicircles, two features. But if we actually run distribution of relaxation time analysis, we see that we are looking at two processes occurring at the first semicircle. So DRT is very important in order to decide with how many circuits to fit our impedance data. As I said, at room temperature, it's very difficult to see the convolution of all the processes, but if we actually run electrochemical impedance at low temperature, such as minus 100 degrees, minus 75, we can see that at high frequency, we've got the appearance of a feature in the impedance spectrum. So we can then see the presence of three distinct features. We can then fit our data using a combination of three RCP circuits. One will describe the interfacial processes, one will describe the grain boundaries, and the third one will describe the bulk processes. And if we fit our data, we can end up with value of resistances and capacitance for the three processes. And if we actually take the data recorded at different temperature, we can plot our conductivities as a function of temperature. So interestingly enough, we saw that the total conductivity of gallium doped LLZO actually had two different values depending on the temperature. So a higher value of activation energy at higher temperature, and a very low value of activation energy at temperature below 0 degrees. In order to understand what was going on, we deconvoluted, as I said, bulk and grain boundaries contribution. And if we look at the contribution of the bulk on the total conductivity of the total conductivity Arrhenius plot, we see actually that the bulk doesn't undergo any change in activation energy in all the temperature range. It's got a very, very low value of activation energy. In fact, it's one of the lowest reported in the literature. Initially, we doubt ourselves, so we did some PFG NMR measurement in order to confirm that actually the value of activation energy was the same, and we see that we've got a value confirmed with NMR of 0.14 electron volts. So this means that our lithium move very freely and very easily in the bulk of the LLZO. However, if we look at the Arrhenius type plot for the grain boundaries, we see they also score a change in activation energy. And the total activation energy seems to follow actually the grain boundaries. So we can say that the performances of garnet are actually governed by the grain boundaries. The reason why we do have this change in activation energy is still not very clear. We are carrying out further experiments, but we do have two hypotheses. One, it could be that we do have an eutectic at the grain boundaries of lithium, aluminum, gallium, oxygen, which can actually undergo a phase transition at temperature below 0, for instance, going from a glassy phase to a crystalline phase. Or it could be that we are actually looking, or the grain boundary is dominated by proton or electron charge carriers. There is an undergoing study. However, with the amount of data that we had, we decided to do a little bit of statistics and see how different samples actually could behave electrochemically. And in this graph in here, I'm comparing the activation energy for bulk and grain boundaries for a set of 3 samples. We have got etched, polished sample, and a polished sample aluminum-free that was actually synthesized in magnesia crucible. So we are ruling out the presence of aluminum at the grain boundaries. And if you look at the bulk seems not to be affected much by the amount of aluminum in the sample. However, if we look at the grain boundaries, we see a consistent and a sensible decrease in the activation energy for the aluminum-free sample. So again, they led to some questions. So it's actually the amount of aluminum that we've got in the grain boundaries that can have an effect on the activation energy. And if that is what is happening, can they have an effect on the electrochemical performances of garnet? I mean, if we change the composition of the grain boundaries, can we actually play with the critical current density for dendrite formations? And to investigate that, we actually took a few samples. Some samples were gallium doped. So we've seen that even in the gallium doped, we do have a tiny amount of aluminum that segregates at grain boundaries. But then we compare the gallium doped with aluminum doped samples. So in the aluminum doped sample, we replaced completely the gallium with aluminum. So we are expecting to have a lot of aluminum at the grain boundaries. And we actually, if we compare the electrochemical performances and the galvanostatic cycling for gallium-doped LLZO and aluminum-doped LLZO, we saw that systematically we had a critical current density, which is the current in which dendrite forms and the cell short circuit. For aluminum-doped, it was consistently of 0.10 milliamp over centimeter square. But interestingly, for gallium, it was consistently 0.16 milliamp over centimeter square. So we do actually have an increase of about 60% in the critical current density. So by doing this experiment and by showing you this result, I've just shown you how different grain boundary composition can affect the dendrite nucleation and propagation. And so how, if we change the grain boundary composition, we can actually target an engineering of the material. To conclude, I want to leave you with some take-home messages. So we saw at the beginning of our presentation, my presentation, the thermal etching on LLZO pellet leads to a cleaning process, so leads to the removal of lithium carbonate from the surface of the pellet, and we can then achieve a better contact between metallic lithium and solid electrolyte. But we also see how the thermal etching can also lead to a more homogeneous cation redistribution in the on the surface of our samples. We also see how local inhomogeneity can affect the electrochemical performances of garnet electrolyte and how they can have an effect on the activation energy of grain boundaries. And by playing with the amount of cation at the grain boundaries, we can actually tune the critical current density for dendrite formation, and in that way do a targeted engineering of materials. So hopefully we will be able in the near future to enable the use of garnet electrolyte in commercial devices. I cannot leave you without a final question. That is actually, can we understand even further? And the answer to that question is actually yes, we can. We can also because in Imperial, now by a project funded by the IPSRC and led by Ainara, we could actually build a custom-made plasma-focused ion beam SIMS. There is a unique instrument. There is no instrument like that in the world. It's called when it will be up and working, you will have a spot size of about 25 nanometers. So you can understand that we can look at very small features. Another unique thing is that it's got a simultaneous positive and negative ion detection. So we can analyze positive and negative ions on the exact same spot of the samples. So this actually will allow us to investigate even further, for instance, grain boundaries, have a more detailed investigation on the chemical composition. And for instance, if we take advantage of the microstructure of our pellet, where we've got very big grains, we could perhaps start milling pillars in which, for instance, include a grain boundary, or mill a pillar in the middle of the grain, so we can also do an electrochemical impedance analysis much more accurate. So we can take into account just one grain boundary, two grain boundaries, and so on. That is something that we start doing. Actually, we compared just the bulk by milling a micropillar of aluminum LLZO and gallium LLZO, and we confirmed that gallium LLZO is actually an higher lithium mobility when compared to aluminum. So please watch this space. And to conclude, I would like to thank you all for your attention on behalf of Ainara and myself. I'd like to acknowledge the funding that we had in order to carry out the work that I've showed you. And I would like to thank our Ainara's group, in particular Rowena, Richard, my friend Andrea, for the contribution that they gave to these talks, and all the other group members. And last but not least, the electroceramic materials group in Imperial for the support over the years. And I'm just going to leave you with these slides in case you would like to read a little bit more about what I've been talking to you today. And we are now open to take questions.
Thank you very much. So we have quite a few questions in the Q&A section. So I'll start with this one. Which is the best synthetic method to obtain high ionic conductivity for a garnet electrolyte?
Do you want to
go ahead? Or?
Yeah, I can. Well, we notice actually the garnet with the ionic conductivities that Ainara was referring to, which is 1.3, if I'm not wrong, millisiemens over centimeter, was actually achieved by salt gel method. So we actually are using salt gel method. Yeah. There could be other methods to synthesize garnet, for instance, solid state routes. But we have seen we've got now developed a consistent salt gel method to synthesize them.
Can I add that one of the most important things is to avoid moisture? So we do everything in a glove box, and we have a furnace coupled to the glove box. I think there is a question also about thermal etching. We do everything in the glove box, and that is very important because moisture reactivity degrades heavily the conductivity of garnets.
So we actually do have a question about the glove box. It says, how do you perform the thermal etching inside the glove box?
We do have a custom-built glove box that was provided by Embrau. So we do actually have a furnace which is attached to the glove box. So when we open the furnace, we actually open the furnace inside the glove box. So the sample undergoes a thermal treatment without seeing any ambient air.
Great. So there's another question. If you are able to engineer the interfaces, possibly create vertically aligned tube-like interfaces to further enhance the improvement?
It's a very, very nice question. Do you want to go ahead?
Well, I mean, we have that in mind, absolutely, because also it will allow you to have a higher surface area, like a 3D interface, but also that it has a low tortuosity, and therefore, I mean, it's one of the things that we want to try to develop. The problem with the garnets is, as I said, that they react very much with moisture and CO2, and there are several processing techniques that we are not able to use so easily. Although there are ways of doing it, and yeah, it's a very interesting point.
I think if I can just add that it has been proved actually previously in the literature that if you actually 3D engineer the electrolyte, actually, as Ainara was saying, you can increase the contact area and the current density, and the pellets can actually, and the material can actually withstand higher critical current density. So it's one of the ways to go forward.
So another question, did you consider measuring the residual stress of garnet electrolyte after sol gel powder from, I believe, with etching some of the residual stress that may be released, and with thermally coupled etching, the electrolyte would be more stress-free and attain stability, therefore have lower resistance during EIS. Did you observe any change in average grain size of garnet before and after thermal treatment?
No, I mean, you have to consider that we do the sintering at 1150 for 6 hours, and the etching is only 900 for 30 minutes. So it doesn't lead to a microstructure change.
Yeah, I can confirm that we never see any change in microstructure.
So this is another question. In 2019, there was a high-profile report that electronic conductivity is responsible for triggering dendrite formation in LLZO. Do you agree? Do you see some evidence of mixed ionic / electronic conductivity at boundaries only?
That is a very interesting question also. Well, at the moment, we don't know. I mean, it's one of the things, that's why we want to be able to do in situ and high resolution impedance analysis. So we can actually analyze difference in conductivities in grain boundaries and grains. And also we couple that to the use of isotopic labeling. So we can also subtract what is the diffusion of the lithium, and therefore try to subtract other possible charge carriers that are within the material. But at the moment, we don't have an answer to that question, but it's a very interesting one that we are trying to analyze.
Yeah, if I can add, it's a very interesting question. I'm aware of the paper that I think Aaron did the question it's referring to. We've seen electronic conductivity as well in our garnets. It's not as high as the Nature Energy paper was reporting, but we definitely see some electronic conductivity there. And I'm now developing, at the moment, we are developing a method that would allow us to actually to monitor the electronic conductivities or the presence of trapped electron in the garnet electrolytes, which could actually be responsible for the nucleation of the dendrites. So if Aaron would like to talk about this further, just feel free to contact me and Ainara, and we will be happy to discuss it further.
So I think we've got time for maybe one more question. Maybe two. Can you increase / control the grain size in order to reduce the interface surface?
We can definitely play with the grain size. In my experience, we haven't actually seen much difference in the interfacial resistance in between larger or smaller grains. But the biggest difference has actually been the thermal treatment. So I'm not entirely sure if that actually would affect match the interfacial resistance.
So I think we just have time for one more question. So in sol-gel method, can't we expect more grain boundaries than in the solid state method?
I mean, it will depend. In sol-gel method, we do the synthesis at a lower temperature, and you will expect a lower grain size, lower grain sizes to start with. But then how they grow is dependent of several factors. We haven't done solid state synthesis of these materials, so we cannot answer from experience to how they impact the microstructure.
Fantastic. So I just wanted to say thank you very much to both of our presenters for such an informative presentation, and also getting through so many of the questions. That was really great. Thank you so much. So a recording of this webinar will be put on the IMSE YouTube channel very soon, and you can find a link for that, including all the other links, in the chat function. I'll just post that again. So the next webinar in this series will be on the 15th of October at 2 p.m. and it will be on the theme of sustainable electrolysis for co-production of hydrogen and value-added chemicals. And this will be presented by Dr. Hugh Lowe. So thank you once again to our presenters, and we hope that you'll have a good day. Thank you so much. Bye-bye.
Thank you very much.
Bye.
Bye-bye. Thank you.